Today we'll look at 13C, discrete random variables, and this is where probability in Year 12 really moves into new territory, so it's really cool stuff. A discrete variable, so let's go through what the word discrete means, can only take certain values and no values in between. So it's often countable. So number of heads when a coin is tossed 3 times, you might get 0, 1, 2, or 3. Number of red cars on the road, there goes 1, there's another one, 2, there's another one, 3. So we're counting the number of. They generally deal with number or size, and note that these values do not need to be whole numbers. So I could say how many people came into the building wearing size 9.5 shoes. Discrete random variables are random as its value is determined by the outcome of a random experiment, e.g. tossing a coin 3 times or 2 dice rolled simultaneously a number of times. Now, some conventions. Random variables are expressed as capital letters, so X, Y, or Z, A, B, C, doesn't really matter. Okay, the convention is we usually start with X, and the value that they can take on is represented by lowercase letters, and we pair them up. So capital X is the random variable, and lowercase x is the values that the random variable can be. And what they can be will depend on what we're looking at. So Y would match up with Y, Z would match up with Z. The other type of random variable is the continuous random variable, and we do them in chapter 15 and 16 actually. These generally deal with quantities which can be expressed, which can be measured, such as mass, height, or time. Okay, so continuous things. Right, so let's have a look at an example. Let X represent, so we got capital X here. So X is the random variable, the number of tails obtained in 3 tosses of a coin, I presume. Right, so list the sample space. So the way I try to get the sample space here is not by thinking it through, because I always do as many as I can and then spend 10 minutes trying to find the missing one. So I'm going to get the tree diagram to produce it for me. Okay, so let's process the tree diagram so we can get head, 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 tail. You might want to double speed me at this point. Head, tail, head. Head, tail, tail. Tail, head, head. Tail, head, tail. Tail, tail, head. And tail, tail, tail. So there's 1, 2, 3, 4, 5, 6, 7, 8. And 1, 2, 3, 4, 5, 6, 7, 8. Alright, so we've got all 8 possible outcomes there. Right, complete the table below, which displays the values the discrete random variable can assume and the corresponding probabilities. So we've already got the possible values X can be. Now let's remember what capital X is. X is the random variable. The number represents the number of tails obtained in 3 tosses. We could get 0 tails, we could get 1 tail, we can get 2 tails, or we could get 3 tails. So you don't need to write them in, but that's just to remind me what X actually represents. It's the random variable can be 0, 1, 2, or 3. It can't be any other values, because like how can you get 4 tails if a coin is tossed only 3 times? How can you get -1 tails if a coin is tossed 3 times? So it's only 0, 1, 2, or 3. Right, let's work it out. So 0 tails is this one here. That's all heads. And there's a 1 in 8 chance of the random variable X taking on the value 0. Now we could get 1 tail here, here, and here. So that's 3 in 8. We could get 2 tails there, there, and there. 3 in 8. And of course we can get all tails, hit the jackpot. 1 in 8. So let's just go through and try to understand what this means, because I think that that's the part that students find most difficult, is actually interpreting the notation. So X denoted a random variable, in this case the number of tails obtained in 3 tosses. Now again, it's important that we look at the reference point for each question and see how the random variable is defined, because for each experiment it will be different things. So X denoted the random variable, the number of tails obtained in 3 tosses, and lowercase x, the value which the random variable can take. Thus the probability can be denoted probability that the random variable equals a particular value x. The probability of the random variable is a function of the value which the random variable could take. So we also say this is p of x, i.e. it becomes a function. So we pop 0 in, okay, pop 0 in, and out pops an eighth. Pop 1 in and 3/8 pops out. Pop 2 in and 3/8 pops out. Pop 3 in and 1/8 pops out. So we consider it a function as well. So what does the probability that the random variable equals 2 mean? Well, that basically means what is the chance that the number of tails is 2? And the answer, 3/8. Okay, that's this one here. So what's the chance that the random variable takes the value 2? The answer is 3/8. Alright, so let's just have a look at some properties of discrete random variables by examining this VCAR question from exam 2. So, close inspection of the tail above shows important characteristics which satisfy all discrete probability distributions. So this is important that we know this. The value of p of x, and that's this thing here, probability that the random variable is one of these values here. We also can say that that's p of x. So we can say that that's p of x and replace it. Is greater than or equal, this is really important, greater than or equal to 0 and less than or equal to 1 for every value of x. Okay, so these probabilities here have to be a value between 0 and 1, but can include 0 and 1 themselves. That's important. The sum of all values of p of x must be exactly 1. That is, if you add that, and that together, it equals 1. Let's just see if VCAR wrote a legit question. 0.5 plus 0.25 plus 0.2 plus 0.05. Yay, they got it right. To determine the probability that the random variable takes on a value from the interval a to b, let's just say 1 to 3, including the values a and b, the values of p of x from a to b are summed. So in this case, from 1 to 3, we would add together that, and that. And that would be our probability over the interval 1 to 3. And that's just it in summing notation. So discrete random variables can be graphed because what we've got is a function. As these random variables, these values go into the function, so 0, 1, 2, 3. So the random variable can take any of these 4 values here. It pumps out these probabilities. So basically, it's actually 4 points on the Cartesian plane. These dots, I'm not sure whether they're conventional or not. I think it's fine just to graph the point itself, but I think the dot just indicates that this is for the value 0 and nothing else. 1 pumps out 0.432, etc., etc. If you graph it, don't link them up with a curve. So don't do this, because that implies that 2.5 gives you a value and it doesn't. Okay, this function exists only at 4 points on the Cartesian plane. 0 there, 1 there, etc., etc. Okay, so state why the following 2 probability distributions are not discrete probability distributions. Okay, so that is actually okay. So we can get the random variable to take on the value -2. What we can't do is get a probability that is less than 0. So that is the problem. So we're going to say that probabilities must be an element of 0 to 1. Remember, we can get a 0, we can get 1, so that's perfectly allowed. Okay, what about this one? Well, again, a lot of people will look at that and go, that's bad, but a random variable can take the value -1. What it can't take is if these probabilities don't add to 1, and that's going to be the issue here, because that, so 0.2 plus 0.1 plus 0.3 plus 0.3 is not equal to 1, therefore not, let's just see what, not a discrete prob distribution. Okay, so it's perfectly allowable for a function, just not a probability distribution function. Okay, so the following is a discrete probability function distribution. That implies that that plus that plus that plus that plus that equals 1 if they're telling us it is a discrete probability function or distribution. So we can find the value of k by going 5k plus 6k plus 4k plus 3k plus 2k equals 1. That's 11, 15, 18, 20. K equals a 20th. So find the probability that the random variable takes on a value larger than 2. That's saying, what's the probability that the random variable is 3, 4, oh, what am I doing, 5? There is no 5. So we'll pull the pin there. Okay, so that's going to be 3, and we just found out that k is a 20th. So 3 lots of 1/20th is 3/20ths, plus 2 lots of 1/20th is 5/20ths, or a quarter. Alright, so back to this question. The number of pets owned by each student in a large school is a random variable with the following discrete probability distribution. So this is what it looks like. If 2 students are selected at random, the probability that they own the same number of pets is. Alright, so we've got student 1 and student 2, and what we're looking for is the chance that they have the same number of pets. So student 1 has 0, student 2 has 0. So that's can't get the words out. That's a possibility. That's the same number of pets. So student 1 goes, I've got 0 pets, and student 2 goes, I've got 0 pets. Wow, the number of pets we have is the same. Okay, the same. So they could have 1 and 1, they could have 2 and 2, they could have 3 and 3. So what we'll do is we'll work out the chance of having no pets and then no pets, 1 pet and then 1 pet, 2 pets and then 2 pets, 3 pets and then 3 pets, and then add those together. So the way to think about this is like a tree diagram. Okay, so we have 0, 1, 2, 3, followed by 0, 1, 2, 3. So we'll be looking at that situation, then 1 and 1, then 2 and 2, then 3 and 3. So 0 would be 0.5 and 0.5. 1 and 1 would be 0.25 and 0.25, etc., etc. So for this one here, I need to churn this one out using my calc. Well, it's probably faster. I could do it by hand. 0.25 times 0.25. 0.2 times 0.2, 0.05 times 0.05. Alright, that's a good sign. Okay, this belter was worth 3 marks with 32% of the state obtaining full marks. So question 8 of exam 1's probably 1 or 2 questions maybe after this one. So this is some good gear here, and 3 marks is a lot of marks. So remember, paper 1 is worth 40 marks. Okay, so this is worth 3 marks. In fact, what's that as a percentage? I don't know why I'm doing this, but yeah, let's just do it. 7.5% of your mark came from this question. So let's see how it works. Has a distribution that looks like this. Find the value of p. So we know that p squared plus p squared plus p on 4 plus 4p plus 1 on 8 has to equal 1, because they're telling us, hey, this is a probability distribution. All right. Now let us put these all over 8. So I'm going to say that this is going to be let's put them together. 2p squared plus so times 2 times 2, 2p on 8 plus 4p plus 1 over 8 equals 1. Probably should have done this at the same time. So it's currently over 1 times 8 times 8. So we've got 16p squared over 8 plus 2p over 8 plus 4p plus 1 over 8 equals 1. Alrighty, so what I'm going to do is note there's no negatives here, or this is not subtract a negative, so I'm not worried about that. I'm just going to multiply all the terms by 8, giving us 16p squared plus 2p plus 4p plus 1 equals 8. Right, collect up your like terms. 16p squared plus 6p, that's plus 1, subtract 8 is negative 7 equals 0. So believe it or not, we're in probability here, and we've just hit a quadratic function. Okay, so factorizing this looks pretty ugly, and I reckon a lot of students would have gone to the quadratic formula at this point. But I reckon this will churn out quite nicely. Well, it has to. It's going to be 4, 4, 8, 2. Is that 14? 8 is 6. Got it. So that is it's 2 7s are 14. That's going to be the negative. So it's going to be 8p plus 7. 2p take 1 equals 0. P equals negative 7 on 8, and p equals a half. But p greater than or equal to 0, therefore p is equal to a half. So we're going to reject that one there. Okay, so guessing, on 3 marks for that, 1 mark for some attempt to put together that. Another attempt maybe, or like getting out the quadratic formula might have been the 2nd mark there, or the quadratic formula, the quadratic function, and then other mark there for rejection and acceptance of a half.
Okay, so for this one, we've got a random variable x representing the number of chocolate chips in a certain brand of biscuit. And it's known to have the following probability distribution. So 2 chocolate chips, 1% chance, 3 chocolate chips, 25% chance, 4, 40%, etc., etc. So seems logical. There's a small chance that you might get a biscuit with 2 chocolate chips only. This would cause a fight amongst my kids. 7 chocolate chips, this would also cause a fight if someone got this many, but there's only a 2% chance of those. Most of them are going to be somewhere in the middle there. Okay, the first thing we want to find out is find the probability that the random variable can take on a value greater than or equal to 4. Okay, so we'll say that probability of x greater than 4 or equal to 4 is the probability that x is equal to 4 plus the probability that x is equal to 5 plus the probability that x is equal to 6. Okay, you don't have to write these things down, but I just think they're good for your notes. So what's that? 0.74. All right, B. Probability that the random variable is greater than or equal to 4. Given that we know that the number of chocolate chips is greater than 2. Okay, we know that the biscuit is going to have more than 2. What's the chance it's got more than or equal to 4? Okay, so for this one here, what we're going to do is say that it's the probability that it's more than 4, probability that x is equal to 4, plus the probability that x is equal to 5, plus the probability that x is equal to 6, plus the probability that x is equal to 7 over, so this one here was over all of it. What we'll do is we'll shrink the sample space down so that it is 1 take away the probability that the random variable is equal to 2. All right, so that is going to be 0.74 over 1 remove 0.01, which is 0.99, and you'll need to write that as 74 over 99. Okay, C. This is a tough one here. So probability that the random variable is less than 5, given that the random variable is greater than 2. Okay, so less than 5 means probability that x is equal to 2, plus the probability that x is equal to 3, plus the probability that x is equal to 4, over the probability that it's greater than 2, which is 1 take away the probability that x is equal to 2. But we know that it's more than 2. So this one here is actually not worth working out, okay, or not worth including here, because the probability that the random variable is less than 5, given that we know that the random variable is greater than 2, means that it's only going to be 3 or 4, because we know that this can't happen. So what we'll do, all right, so x equals 3 is 0.25 plus 4, what's 4 again? 0.4 over 0.99. So that is 0.65 over 0.99, which is 65 over 99. All right, so there's your 13C questions right there.